Now, guys, welcome back again. By the time I left, we're looking at atomic notation. How do we write an atom? To remind ourselves, we had said it is represented by this, where A is the atomic mass, and then Z is the atomic number. This one we say is the species or the type of atom we are talking about. This is the atomic number. Now, this is how we denote an atom. We are going to look at another thing that we are going to call, it is also denotation. How do we denote isotopic notation? How do we write isotopes? But before we learn how to write the notation for isotopes, what is an isotope? Now, an isotope is defined as an atom of the same element, with the same atomic number, but different atomic mass due to different number of neutrons. That we are going to find an atom of a given element. It has the same atomic number, but different atomic masses, simply because it has a different number of atoms. I mean, different number of electrons. So we can either define an isotope as, we can say an isotope is an atom of the same element, with the same number of protons, but different number of neutrons. That we shall call it an isotope. Now, another thing, we are going to look at what we call isotope. Now, what is the isotope? If an atom exists in different forms, having the same number of protons but different number of neutrons, then we say that such an atom exhibits what we are calling isotope. We shall say it is exhibiting what we call isotope. And we are going to say isotope is the existence of an atom of the same element, with different mass but having the same atomic number. So that is what we call, or we refer to as the isotope. That's what we call isotope. Then, we are saying we are looking at the notation of isotopes. How do we write an isotope? How do we denote it? We are still following the same procedures as before. We're going to follow the same procedures that we used previously, where we say that A denotes atomic number, assuming this is our same atom. That is how we do not we are going to write it. Now let us look at examples of atoms. Then we look at the various isotopes. Now, we are going to begin with, let's look at the elements that exhibit isotope. We begin with hydrogen. Hydrogen is denoted like that, and when it is like that, we say this is the protein. Or the reason we call hydrogen a proton, it can have mass number 2, and here we call it deuterium. It can have 3 H1, and here we shall call it tritium. We look at another element called the carbon. Carbon has various isotopes. We have carbon 12. This one is called carbon 12, and then carbon 14. This is carbon 14. Look at another element that exhibits isotope. We look at chlorine. We have chlorine 35. This one is called chlorine 35. We also have chlorine 37. The other element shall have element here. We look at this one here, we can call them isotopes. Okay, notation. So here I'm going to have the notation, and then here I will look at the isotopes. Another element that we're going to look at is called uranium, and you know that this is useful in making the nuclear power and nuclear weapon. We have uranium 3, 4, 92. So this is called the uranium 234. We have uranium 35, 92. So this will be uranium 235. We have uranium 292. So the isotope of uranium. This will be uranium-238. And there are other elements that also exhibit isotopy. Now, if we can expand on this, for example, if you look at protium, it has 1 proton, it has a 0 neutron. So for that reason, it is at times called a proton. This one is at times called a what? A proton, because it only has 1 proton. This one, we are saying that it has a mass number of 2, meaning it has 2. It has 1 proton and 1 neutron. This is tritium. We are saying that it has 2 protons and 1 neutron. So, in fact, it has 1 neutron and 2 it has 2 neutrons and 1 proton. The same case everywhere. So all these elements exhibit isotopy. And we are saying a scenario where an atom of a given element shows up with different mass numbers, but the same atomic number, we say that such an atom is exhibiting what we call isotopy. We call that what? Isotopy. And what you should know that these isotopes are in most cases radioactive. That isotopes are radioactive. The isotopes are radioactive in nature. Now, why are they radioactive? Or what is radioactivity first? Radioactivity is the spontaneous disintegration of a radioactive nuclide by emitting either alpha, beta particles, or gamma rays plus energy to obtain stable atoms out of them. So that process is called radioactivity, and we shall see it ahead. That is radioactivity. Now, for example, these isotopes are very useful. For example, carbon-14 is used in carbon dating, which carbon dating is used in determining the age of fossils or of remains. For example, in primary and O-level, we are told that the skull of Aleman was got at Olmsted, and when they tested it, it showed that this Aleman had existed for some good millions of years. So you see, we are now using radioisotopes to detect the age of a dead material. And how is it done? How it is done, we use the decay law that we shall see ahead. But if I can brief you a little, the decay law states that the rate of disintegration of a radioactive sample is always directly proportional to the amount that is left at a given time. So guys, let's stop here for now. After here, we are going to look at ionic formation and the nomenclature. How do we name the compounds that we shall be using within this topic? Thank you very much. We meet in the next meeting. Thank you.